Welcome to the Deep Dive, the only place where we take stacks of complicated research and distill it down to the essential, the surprising, and the truly mind-blowing. If you have ever bought a carton of milk, you know the name we are focusing on today, Louis Pasteur.
And if that's all you know you are missing, I mean, just the most incredible scientific journey of the 19th century.
Right.
Pasteur wasn't just about food safety. He was a singular revolutionary who moved, seamlessly from the abstract world of molecular chemistry to the practical, life-saving world of public health.
He bridged fields that had just been operating in total isolation before him.
Completely.
And our mission today really is to unpack that for you. We're going to look at his career through four main pillars.
Yeah, for huge pillars. It starts with chemistry, right? This completely unexpected place.
Right, molecular chemistry. Then we move into the stuff people know a bit more about, fermentation, germ theory.
Pasteurization, of course.
Of course. And then disease prevention. This is where it gets really intense. The silkworm crisis, his pioneering work in vaccination.
And that's where it gets really dramatic.
Yeah.
And then finally, we have to talk about the controversy.
We do, because his legacy is not as simple as the milk carton makes it seem, especially with the revelation of his private notebooks.
No, not at all. But it is a legacy that defines modern biology. When we talk about Pasteur, we're talking about a titan.
One of the undisputed founders of modern bacteriology.
Exactly. He's called the father of bacteriology, and he often shares the title father of microbiology with his great rival, Robert Koch.
And the work itself, I mean, the vaccines for anthrax and rabies alone are credited with saving millions of lives. They shifted global demographics.
On a scale that was just unimaginable at the time.
To really understand that scale, you have to appreciate the sheer distance he traveled. A career that starts with, looking at crystal shapes under a microscope, and ends with injecting a virus into a child who was mauled by a rabid dog. It's an extraordinary trajectory.
It really is.
Okay. Let's unpack this journey, starting with the very surprising circumstances of his beginning.
So Pasteur was born in Dole, France in 1822. And his background was intensely humble.
No silver spoon here.
Not at all. His father was a poor tanner, Jean-Joseph Pasteur, who had been a sergeant in Napoleon's army. There was no inherited wealth, no academic family line to speak of.
And when you look at the towering figure he became, it's genuinely startling to learn that his early academic career was just, it was marked by struggle and mediocrity.
Yeah.
It was not some wonderkind who was destined for the laboratory.
Far from it. As a boy, his interests were mainly creative and outdoorsy. He loved to go fishing, and this is the surprising part. He was a really talented sketch artist.
Really?
Oh, yeah. We still have a collection of his early portraits and pastels of his family members. He seems to have had this, meticulous attention to detail even back then, but he's applying it to art, not to equations.
And academically, he hit a few roadblocks, right?
He did. He failed his first examination for the École Normale Supérieure in 1841. He eventually got his Bachelor of Science in 1842, but even then, his grade in chemistry, the field where he would become a legend, was described as mediocre.
Just mediocre.
Yeah.
It's often suggested that he might have been dyslexic and dysgraphic based on his struggles with written language.
It's a really interesting hypothesis.
Yeah.
That a man who struggled with the written word found his true voice in the physical world of experimentation and visualization.
He just kept at it, though.
He persisted. He finally entered the prestigious École Normale Supérieure in 1843 after improving his standing. But his greatest intellectual breakthrough didn't happen in biology at all. It was in the highly abstract field of structural chemistry.
And we're not just talking about a good paper. Some have described this as his most profound and most original contribution to science.
That's it.
This is the molecular breakthrough of 1848, dealing with tartrates and the concept of isomerism.
That's right. And the problem had stumped chemists for decades. They were looking at two different forms of tartaric acid.
Okay.
One was derived naturally as a byproduct of winemaking. The other was synthesized in a lab. When they analyzed them chemically, they were identical. Same elements, same proportions. They should have been the same molecule.
But they weren't. And the difference was only visible when you expose them to polarized light.
Exactly. Light, it oscillates in all directions. When it's passed through a polarizing filter, the light waves are restricted to a single plane. The natural form of tartaric acid had this really curious property. When you dissolved it, it rotated that plane of polarized light to the right. This was called dextrorotatory.
And the synthetic one?
The chemically synthesized version did nothing. It was optically inactive.
That's the puzzle, isn't it? Two compounds, same formula, but one twists light and the other doesn't. Why? I mean, scientists like Berzelius and Liebig were completely baffled.
They were. They believed that if the composition was identical, the properties had to be identical. It was a fundamental assumption.
And this is where Pasteur's background in crystallography becomes his superpower.
It really does. He was studying the salts of racemic acid, that's the inactive synthetic form, and he observed that the mixture contained two distinct types of tiny crystals.
Wait, so the synthetic mixture already had both forms in it. How did he even know to look for two separate crystal types if he didn't know about chirality yet?
He was building on the work of the French mineralogist René Juste-Haüy, who had shown that certain crystals that rotated light were asymmetrical. Pasteur noticed that the crystals in this racemic mixture, while identical in composition, were non-superimposable mirror images of each other.
Like your left and right hand.
A perfect analogy. They are reflections, but you cannot perfectly lay one on top of the other. They're different in a three-dimensional way.
So he sees this, and then he has to act on it. He must have spent agonizing hours physically separating these microscopic crystals.
It was an incredible, painstaking effort. He used only forceps and a microscope, sitting for hours, manually separating the right-handed crystals from the left-handed ones. It was purely based on their physical, visual asymmetry.
And the result, once he put the separated piles into a solution, that must have been the true aha moment.
You can just imagine it. When he dissolved the right-handed pile, it rotated polarized light to the right. Dextrorotator.
On a left-handed pile.
Rotated light to the left.
Oh.
Levoritator. And when he mixed them back together in equal parts, just like they were in the original synthetic batch, the opposing rotations canceled each other out.
Making the solution optically inactive. Mystery solved.
Completely solved.
So what does this all mean for the bigger picture? I mean, the significance here is enormous.
It's massive. This experiment in 1848 was the very first demonstration of molecular chirality. The idea that molecules can exist as these non-superimposable mirror images, we call them enantiomers now.
It was the first real explanation of isomerism beyond just basic composition. It basically forced chemists to start thinking in three dimensions.
And the impact on structural chemistry was immediate, but think about the impact on medicine today. A drug's efficacy often depends entirely on whether it's the right or left-handed version of a molecule.
Right. Sometimes one version works and the mirror image is inert or even toxic.
Exactly. And Pasteur, this poor tanner's son, laid the absolute bedrock for that entire field of understanding. He even showed that life itself, specifically the mold used in fermentation, had a preference for one form.
The natural dextrorotatory one.
Yes, life is chiral. And that observation, that connection between the abstract world of crystals and the living world of biology, is the exact transition that defines the next stage of his career.
So Pasteur's shift from crystallography to biology wasn't just, abstract curiosity. It was intensely practical.
Oh, and economically vital. In 1856, he was dean at the University of Lille, which is a big industrial city, heavily involved in alcohol production.
And a local wine manufacturer, a man named M. Bijot, came to him with an industrial crisis.
A huge crisis. His beetroot alcohol kept souring, and his wine was spoiling way too easily. He was losing money hand over fist.
So Pasteur takes this problem from a beer vat and essentially turns it into the germ theory of disease. But he starts by tackling the prevailing theory of fermentation, which was basically chemical dogma at the time.
It was scientific gospel, championed by huge names like Liebig and Berzelius. Their theory was that fermentation sugar turning into alcohol was a purely non-living chemical process.
A process of decomposition.
Exactly, or putrefaction. They saw the yeast as just a protein compound in the process of decaying, and they thought that decay somehow kicked off the decomposition of the sugar.
And Pasteur showed this theory was completely backward. How did he prove it was life, not decay, that was responsible?
He used his microscope, the same one he used for looking at those crystal facets. He looked at the fermenting liquid and realized that the yeast, which everyone thought was just a chemical precipitate, was actually a living organism.
It was alive.
It was alive. And through these meticulous experiments, like cultivating yeast in media that was free from any external contamination, he proved that living yeast was solely and directly responsible for converting sugar into alcohol. Fermentation was a biological process, a life process.
Not just a simple chemical breakdown.
Not at all.
And this is where he makes the leap from how alcohol is made to how things spoil. He extends that finding to the sour wine problem.
Exactly. When the wine went sour, he looked under the microscope again, And he found that when a different microorganism, usually a little rod-shaped bacterium instead of the spherical yeast, contaminated the wine,
The fermentation went wrong.
it went completely awry. Instead of producing ethanol, this contaminating microorganism produced lactic acid, and that's what made the wine sour and undrinkable. This was the direct, undeniable link. Microbial growth causes product spoilage.
It sounds so simple to us today, but in the mid-19th century, this was radical. It was moving the entire scientific world away from these vague ideas of bad air or spontaneous decay and into the measurable world of living microbes.
And what's also fascinating is the nuance he found. This research led to a major side observation in 1861, which we now call the Pasteur effect.
Okay, what's that?
He noticed that yeast fermented sugar at a significantly lower rate when it was exposed to air aerobically compared to when oxygen was absent anaerobically.
So oxygen was actually slowing the fermentation down?
Yes. He figured out that when oxygen was present, the yeast could respire more efficiently. It needed less sugar for energy, so it used more for growth rather than for fermentation.
But when you took the oxygen away,
It had to switch to the much less efficient anaerobic process of fermentation just to survive, and so it had to chew through sugar much, much faster. It was this beautiful illustration of microbial metabolism.
and it completely demolished the old decomposition theory.
It did. And all of this work led to his most recognizable invention. If invisible microorganisms cause spoilage, then the solution is to kill them. This is the birth of pasteurization.
A simple, elegant industrial solution.
It's exactly. For the wine and beer makers who were losing fortunes, Pasteur recommended just heating the liquids. Pasteurization, named after him, involves heating a liquid to a controlled temperature, say between 60 and 100 degrees Celsius, for a specific time.
And that heat is enough to kill most of the bacteria and molds, the contaminating agents, without ruining the product's flavor.
Right. He and Claude Bernard completed testing even on things like blood and urine samples in 1862, and the process was patented for wine in 1865. The economic relief for the French wine industry was immediate and massive.
But the truly colossal leap wasn't saving wine, it was the application to medicine.
That's the real breakthrough.
If microorganisms could ruin beer and sour wine, what happens if those same microorganisms get into an animal or a human?
That was the revolutionary idea. The idea that invisible germs cause disease. The germ theory had been proposed before, but Pasteur provided the irrefutable evidence straight from the laboratory and the industrial vat.
And the ripple effect was instant. This connection profoundly influenced Joseph Lister, the British surgeon.
Lister immediately applied the principle to his work. If germs cause spoilage, they must cause surgical sepsis. So Lister developed antiseptic surgical methods, using carbolic acid, to prevent those invisible organisms from getting into the patient's body during an operation.
And it revolutionized surgery. It dramatically reduced mortality rates from infection.
It did.
So we've moved from tartaric acid crystals to antiseptic surgery in just over a decade, but the next stage of his career involves tackling, really, the philosophical fight of the age.
That's a great way to put it. The work on fermentation was about life causing change. The next big battle was about how life starts.
And this was one of the most contentious, high-stakes debates of the 19th century. Spontaneous generation.
For our listeners, spontaneous generation was this ancient doctrine going all the way back to Aristotle. The idea that living organisms could just arise, spontaneously from non-living matter.
Maggots from spoiled meat, mice from old rags.
Right. Or, in the 19th century context, life just springing forth from a sterilized liquid simply by being exposed to air.
And this idea was fiercely championed by figures like Félix Archimede Pouchet.
Pouchet was the director of the Rouen Museum of Natural History, and he argued forcefully that air, even pure air, possessed some kind of creative, vital force that could spontaneously generate life.
This wasn't just a quiet academic argument. The implications were enormous, touching on the origins of life itself.
So big that the French Academy of Sciences wanted it settled. In 1860, they offered the Alhumbert Prize, a substantial 2,500 francs, to whoever could definitively prove or disprove the doctrine.
And Pasteur went right after that prize.
He did, and he won it in 1862 through a series of experiments that are just legendary for their clarity and elegance. His approach wasn't to argue philosophy. It was to use the microscope and controlled contamination to prove where this spontaneous life was actually coming from.
And it was coming from the environment.
Exactly. He first replicated the classic experiments. He showed that if you sterilized a liquid broth by boiling it and then sealed the container completely, Nothing grew.
Okay, so that suggests that something from the outside, presumably the air, was necessary. But how do you prove it's dust in the air and not the air itself?
He had a stroke of genius with his altitude tests. He took a series of flasks with boiled, sterilized broths and carried them to different altitudes. He went up to the high purity of the Mer de Glace glacier in the Alps, but he also did tests in the contaminated air of Paris.
And the method was just to open the flasks for a moment, expose them to the air, and then seal them back up.
Precisely. And he would count how many flasks subsequently showed microbial growth. Down in the polluted air of the Paris streets, nearly all the flasks quickly showed growth.
But up on the mountain?
High up on the glacier, where the air was demonstrably cleaner and had less dust, very, very few of them showed any growth at all.
That's a powerful distinction. It proved the germs were airborne, attached to dust particles, not some mysterious property of pure air.
Right. The presence of the dust determined the outcome. And then we come to the experiment that sealed the deal. The one everyone recognizes. The swan neck flasks.
The iconic experiment.
It is truly the perfect, definitive experiment. It illustrates the principle with flawless clarity.
So describe the setup for our listeners. What was the key feature of this design?
The flasks were specially designed with these long, curving necks, shaped like an S or a swan's neck. Pasteur boiled the nutrient broth inside to sterilize it. The key was that the neck was open to the atmosphere. Air, the supposed source of spontaneous life, could freely get in.
But the crucial element was gravity.
Yes. As air currents moved in and out, the heavier dust particles, which had the actual germs on them, were trapped by gravity and moisture in the curves of the neck.
So they could never reach the broth.
Never. And for months, even years, the broth remained perfectly sterile. It proved that life doesn't just arise spontaneously. You could have pure air circulating, but without the dust, the contamination never happens.
And the only way to contaminate it
Was to do what Pasteur dramatically demonstrated. You tilt the flask, let the sterile liquid flow down and touch the accumulated dust in the neck, and then tilt it back.
And then microbial growth would begin almost immediately.
Instantly. It was the definitive refutation of a doctrine that had stood for millennia.
He was absolutely justified in his dramatic conclusion. Never will the doctrine of spontaneous generation recover from the mortal blow of this simple experiment.
The concept of biogenesis, that life only comes from life, was established, and the germ theory of disease gained enormous credence.
And that focus on contamination and life from life leads us directly to the next phase, tackling a devastating biological crisis that threatened an entire industry.
The silkworm crisis is such a crucial part of Pasteur's story because it shows him applying abstract microbiology to this massive, messy, real-world economic disaster.
Right. By 1865, two devastating diseases were just decimating silkworm farms across France and Europe. The national silk industry was on the brink of collapse.
This was a political issue as much as a scientific one. A powerful chemist and senator, Jean-Baptiste Dumas, personally called on Pasteur to intervene. This wasn't a lab experiment anymore. This was a national emergency.
So Pasteur spent 5 intensive years, from 1865 to 1870, mostly in Alès, studying this problem. And he had to deal with 2 distinct diseases.
That's right. First, there was pebrine, which was characterized by these cornelia corpuscles and black spots on the worms. And second, flashery, or dead flat disease, where the worms just became soft and flaccid and died quickly.
And this chapter is so important because, unlike the fermentation experiments or the spontaneous generation debate, Pasteur wasn't instantly the genius here. He made significant documented errors at the start.
That's vital to acknowledge. His first major stumble was scientific simplification. He initially believed that pebrine and flashery were either the same disease or at least closely related. He was treating them as one single pathological process.
How long did that last?
It took him 2 years, until 1867, to clearly distinguish between the 2 separate conditions, each with its own cause and its own mode of transmission.
And his second mistake was about the cause of pebrine. Other researchers, particularly Antoine Béchamp, who we'll talk about later, had already suggested the disease was parasitic or microbial, focusing on those corpuscles.
Right. But Pasteur initially rejected that. He saw the corpuscles as just a symptom of degeneration, not the active cause of the illness.
But he did change his mind.
He changed his mind by 1867. He finally conceded that the corpuscles, which we now know are spores of a microsporidian parasite, were indeed the causative agent of pebrine. For flashery, he correctly identified a bacterial component, even though we now think the primary cause is viral.
But for the time, attributing both to microbes was a major step.
A huge step.
And despite the initial missteps, he developed a profoundly effective solution for pebrine that basically saved the industry. What was the method?
It was a simple, yet rigorous quality control measure based entirely on his microscopy skills. He mandated this stringent sorting process, focusing on the mother moth, the female that laid the eggs, or the seed.
So once the moth laid her eggs, what happened?
The moth was immediately crushed into a pulp and examined under the microscope.
Oh, wow.
Yeah. If the characteristic pebrine corpuscles were found in the mother's tissues, the entire batch of eggs laid by that moth was immediately destroyed, not used for breeding.
But if the mother was clean...
The eggs were deemed healthy seed and allowed to proceed.
So this just stopped the hereditary transmission of the disease in his tracks.
Precisely. It broke the cycle of infection being passed from one generation of moths to the next. This simple, systematic sorting method dramatically reduced the incidence of pebrine and rescued the silk industry.
And for flashery.
Prevention there relied more on hygiene, making sure the moths were clean and the silkworms weren't eating contaminated food. It was a massive victory for applied microbiology and disease control, and it cemented his reputation as a national problem solver.
The silkworm work really solidified his germ theory credentials, but the next phase, this is what cemented his position as one of the great medical innovators, the development of artificial vaccination. We know the concept of using a weak disease to confer immunity was already established, right? Edward Jenner's work with cowpox and smallpox almost a century earlier.
Right. Jenner used a naturally occurring, related, but weaker disease cowpox, or vaccinia. Pasteur's revolutionary contribution was proving that you didn't need a natural variant. You could take a deadly pathogen and artificially weaken it, or attenuate it, in the laboratory to create that safe immunity.
And he honored Jenner by applying the term vaccines to these artificially weakened pathogens.
He did. His first successful, though imperfect, attempt at this involved chicken cholera, which is caused by the bacterium Pasteurella multicida.
Ah, the famous story of the serendipitous discovery.
One of the great tales of scientific chance. In 1879, Pasteur's assistants, Emile Roux and Charles Chamberlain, were growing cultures of the chicken cholera bacteria. They went away for a summer break.
And they left a culture sitting out.
They left the culture sitting out, exposed to air, for months. It had been sitting since July, and it lost its virulence.
So when they came back and used this old, weakened culture, what happened to the chickens?
The chickens they inoculated with the old culture got a little sick, but they didn't die. They recovered completely.
Okay.
Then the assistants tried to kill these same chickens with a fresh, virulent culture, which should have been lethal. But the chickens were immune. The prolonged exposure to air had attenuated the pathogen without killing it, creating a protective memory in the chicken's immune system.
That initial observation that the old culture lost its virulence, that was the key insight. But it wasn't a completely smooth process, was it?
No, not at all. While the general principle of attenuation was sound, getting the chicken cholera vaccine to work reliably was difficult. Pasteur attributed the attenuation to oxygen, thinking it interfered with the bacterial metabolism.
But the vaccine itself was later found to be kind of inconsistent?
Yeah, it was later proven ineffective by others. But it provided the essential conceptual roadmap. Pathogens can be artificially weakened by controlling their environment.
And that roadmap led directly to a much greater challenge and a much greater triumph: anthrax.
Anthrax, caused by Bacillus anthracis. It was an economic killer, especially for cattle and sheep, creating those grimly named cursed fields across Europe.
Pasteur's first contribution was environmental. He figured out that earthworms were bringing the resilient anthrax spores up to the surface from the buried bodies of infected animals.
Right. He told farmers to stop burying dead stock in their fields. But developing the vaccine was complex because the anthrax bacillus was different from chicken cholera. It formed these extremely hardy spores.
So just exposing them to air wouldn't work?
Wouldn't touch them.
Oh.
The spores are highly resistant, so his lab had to find another controlled variable. They eventually discovered that by growing the anthrax bacilli at a slightly elevated temperature, specifically 42 degrees Celsius, they could stop them from producing spores.
So that weakened them.
Exactly. The bacteria survived, but their virulence was significantly reduced, creating a safe, live, attenuated vaccine.
Which brings us to the ultimate PR and scientific triumph: the Puy-Lafort experiment in 1881. This was a massive public spectacle.
It was staged drama. Pasteur accepted a public challenge from a local veterinary society. The setup was highly visible. 58 sheep, 2 goats, and 10 cattle. Half were vaccinated with his attenuated culture. The other half, the control group, remained unvaccinated.
And then came the climax. On May 31st,
All 70 animals, vaccinated and untreated, were injected with a highly virulent fresh culture of anthrax. And the world waited.
the public observation on June 2nd must have been incredible.
It was a shattering success. The untreated animals were either dead or dying, scattered across the field. All the vaccinated animals survived, showing no symptoms at all.
The press went wild. Pasteur became an instant global hero.
He did. And he seemed to confirm his claim that this was a superior live vaccine compared to anything that came before. But this is where we encountered the ethical complexity that defines his legacy.
Because he wasn't being entirely truthful about his methods.
He publicly insisted this was a live, attenuated vaccine, which allowed him to dismiss prior work by his rivals. Specifically, a veterinary surgeon named Henri Toussaint had developed a functional anthrax vaccine in 1880 using heat-killed bacilli.
And Pasteur publicly contested his results.
He did. He claimed a killed vaccine wouldn't provide lasting immunity. But the truth, which came out much later from his notebooks, complicates this story.
What did the notebooks reveal?
Historian Gerald Geison's analysis confirmed that for that specific public demonstration at Puy-le-Fort, Pasteur and Chamberlain secretly used a potassium dichromate-killed vaccine, a chemical method conceptually very similar to Toussaint's approach.
So he deliberately misled everyone.
He misled the public and the scientific community about the methods used in that celebrated trial to guarantee success and to defeat his rivals.
It raises such profound questions about means and ends. He achieved a world-saving result, but the method for securing public trust. It relied on a degree of professional deception.
The rabies work represents the final, and I think the most high-stakes, application of Pasteur's methods.
Rabies was a uniquely terrifying death sentence in the 19th century.
Incurable, gruesome, and virtually 100% fatal once symptoms appeared. Just horrific.
His approach to creating the vaccine was novel, mostly because rabies is a virus, and they couldn't culture viruses like bacteria back then. So how did they prepare it?
They used a process called passage. They would grow the rabies virus in rabbits, passing the infection from one rabbit to the next until they had a strain with a consistent incubation period.
Oh.
Then they would harvest the affected nerve tissue, the spinal cord specifically, and hang strips of it in a sterilized dry container. The exposure to air and desiccation would gradually weaken or attenuate the virus over a period of days.
So the longer the tissue dried, the weaker the virus became. This let him create a sort of scale of attenuation.
Yes, a sliding scale. From the least virulent, the oldest, most dried tissue, to the most virulent, which was the newest, least dried tissue. And that system was absolutely critical for the famous first human trial.
The trial of 9-year-old Joseph Meister in July 1885. He had been severely mauled by a rabid dog and was facing near certain death. The decision to intervene must have been excruciating.
It was an unimaginable risk. Pasteur, along with the boy's mother, decided to go ahead. The treatment was complex and aggressive. Meister received 13 inoculations over 11 days.
And the procedure involved starting with the most attenuated virus and progressively getting stronger.
Exactly. Start with the safest, most weakened nerve tissue, and then inject cultures that were less and less attenuated, moving toward the most virulent strains by the end of the treatment.
The idea was to give Meister's immune system time to build protection against the weak virus before introducing the stronger ones.
Right.
And the outcome was one of the great medical miracles of the century. Joseph Meister recovered completely.
And the world immediately hailed Pasteur as a humanitarian hero, a figure comparable to Jenner. But retrospectively, and especially after the notebooks were revealed, the ethical complexity of that decision really came into sharp focus.
What were the main criticisms that emerged?
The first, and most obvious, was that Pasteur was not a licensed physician. He was risking prosecution for practicing medicine without a license.
A huge personal risk.
A huge risk. And crucially, his highly skilled medical partner, Émile Roux, refused to participate in the clinical trial. He argued that the vaccine was not yet sufficiently tested or standardized for human application. Roux's refusal really underlines how premature the experiment was perceived to be.
The second major issue was the preliminary testing. Pasteur publicly claimed he had successfully vaccinated 50 dogs.
Which would have been a pretty robust preclinical trial. However, the private notebooks tell a different story. They suggest he had actually only vaccinated 11 dogs, and the results of those few trials were inconsistent.
So the human application was based on far less data than he publicly admitted.
Far less. He later defended the secrecy by saying it was necessary to control quality, but it fueled deep suspicion.
But what about oversight? Was he entirely alone in performing the procedure?
No, and that's a key mitigating factor. He consulted with two renowned practicing physicians, Jacques-Joseph Grancher and Alfred Vulpian. And it was Grancher, the physician, who physically administered the 13 injections to Meister.
So while Pasteur conceived and erected the treatment, the actual inoculation was performed under medical oversight.
Which likely helped protect him from legal repercussions. But the decision, the moral and professional burden of it, was entirely his own. And the case highlights this immense personal urgency driving his work, which, as we'll see, was terribly, terribly personal.
That personal urgency is so crucial. Before we dive into the rivalries that haunted his professional life, let's just reflect on the personal stakes. Pasteur and his wife Marie had 5 children.
But devastatingly, 3 of them died in childhood, mostly from typhoid fever.
It's impossible to separate that staggering personal loss from his almost feverish drive to conquer infectious disease.
Absolutely. Typhoid is a classic waterborne microbial disease. To lose 3 children to the very microscopic world he was trying to conquer, it must have imbued his entire career with this profound, relentless mission.
And that relentless ambition often came into conflict with other scientists, especially once the veil of secrecy around his work was lifted with the publication of his lab notebooks.
The story of the notebooks is fascinating. Pasteur insisted his family never reveal them. They were held privately until 1971, nearly a century after his birth.
And when historian Gerald L. Geisen finally published his analysis in 1995, it was a bombshell.
It confirmed long-held suspicions. The Pasteur had systematically used deception, selective reporting, and misleading accounts to triumph over his rivals and secure priority.
So let's break down the major scientific disputes that these revelations confirmed, starting with the rivalry in fermentation with Antoine Béchamp.
Béchamp, he's a French physician and chemist who definitely deserves a strong mention. As early as 1858, Béchamp had claimed priority for showing the role of microorganisms in fermentation.
He argued it was a living process before Pasteur published on it.
He did. And he criticized Pasteur's methods and claims throughout his career.
But Béchamp is largely forgotten today. Why did Pasteur win that historical argument?
Well, Béchamp certainly had valid points about priority, but he later went off the rails by developing this complex and ultimately incorrect microzymes theory. He believed all living things were composed of these tiny, indestructible molecular granules that could transform into bacteria.
Okay, that sounds a bit out there.
It was a flawed theoretical framework, and it allowed Pasteur, who focused on simple, demonstrable microbial action, to sideline him and cement his own reputation. Pasteur was ruthless in not citing or acknowledging work that might dilute his own claim.
The other, perhaps more damaging rivalry was the one with Henri Toussaint over the anthrax vaccine.
It was a bitter dispute. As we said, Toussaint developed the first effective anthrax vaccine in 1880 using heat-killed bacilli. Pasteur publicly disparaged this concept, arguing a dead vaccine couldn't provide lasting immunity.
And yet, his notebooks showed that his celebrated Pouilly-IV trial used a chemically killed vaccine which operated on the same principle as Toussaint's.
It was a massive public victory, won by secretly borrowing from his rival's concept without ever providing attribution. It really highlights the intense pressure for priority and recognition in 19th century science.
And we can't ignore the methodological clashes with Robert Koch, the great German microbiologist.
That was less about priority and more about a difference in scientific philosophy. Koch, who had identified the anthrax bacterium and developed his famous postulates, was meticulous. He criticized Pasteur's use of impure cultures and imprecise protocols.
And Pasteur's response?
He defended his results robustly, sometimes accusing Koch of misinterpreting data. This rivalry drove both men to massive breakthroughs. Koch focused on isolation and pure culture, while Pasteur focused on physiological manipulation, like attenuation.
Finally, let's consider his institutional legacy and his personal faith. There's a lasting debate over whether he remained a devout Catholic or became more of a spiritual freethinker.
His family presented conflicting pictures. His son-in-law said Pasteur had absolute faith in God. But his grandson later noted that Pasteur retained only a sort of spiritualism without formal religious practice.
And Pasteur himself?
He was a strong advocate for the separation of science and dogma. He famously said, "Woe to those who want to make them encroach upon one another." He was a man of deep contemplation, but he fiercely guarded the independence of scientific inquiry.
regardless of his personal beliefs, his institutional legacy is absolutely undisputed. The success of the rabies vaccine led to massive global fundraising.
And that fundraising led to the establishment of the Pasteur Institute in 1887. Its initial purposes were to provide rabies treatment and be a fundamental research hub for virulent diseases.
It immediately drew top scientific talent.
It did, including Émile Roux, who, despite his ethical concerns about the Meister trial, established the world's first formal course in microbiology there.
And today, the Institute is this vast international network. 32 institutes in 29 countries, continuing the work he pioneered.
It's the ultimate testament to his impact. As the French academician Henri Mondor summarized it so eloquently, Louis Pasteur was neither a physician nor a surgeon, but no one has done as much for medicine and surgery as he has.
An industrial chemist who became medicine's greatest champion. That was an extraordinary life to unpack. We've traveled from a painstaking experiment proving molecular asymmetry, a cornerstone of modern chemistry, all the way through to establishing public health standards with pasteurization.
And settling the ancient debate of spontaneous generation with the swan neck flask.
And pioneering the entire age of artificial vaccination against killers like anthrax and rabies.
His foundational work is the bedrock of modern life. Every time you use sterile medical equipment, drink safe milk, or rely on a vaccine, you are leveraging the principles established by his relentless efforts.
The invisible world he made visible defines our existence today.
It really does.
So, as you reflect on this extraordinary legacy, we want to leave you with the challenging ethical question that the revelation of his notebooks forces us to confront. Pasteur, driven by ambition and this fierce desire to see his discoveries adopted quickly, used methods of secrecy and selective reporting to outmaneuver rivals like Toussaint and Béchamp.
Those methods, judged by modern scientific standards, they lack integrity. Yet they led directly to breakthroughs like the functional anthrax vaccine and the successful treatment of Joseph Meister, saving untold millions of lives.
So how, then, should history ultimately judge the man? If a scientist's ethical shortcuts lead directly to world-saving breakthroughs, is the resulting immense benefit always sufficient justification for the methods they use?
It's the tension between scientific progress and personal integrity. And it's a question that continues to challenge the moral landscape of scientific advancement today.
Something to consider the next time you see that name printed on your food packaging. That was the deep dive. We'll see you next time.